So you want to know if there's a way to operate an RC vehicle despite disability? Well, by combining an Arduino and an Xbox adaptive controller, there's a way. In this video, we'll show you how. There's two main ways to get an adapted control system to communicate with a remote control vehicle. The first is what you see at the top here, which is where you start with some kind of input system, which we'll talk about more later, the details around that. That connects into the Arduino-based adapter. Following from there, the first option is based on connecting that adapter into the trainer port of a standard radio control transmitter, and then using the transmitter to communicate those messages across to the RC vehicle. So if you already have a transmitter with a trainer port on the back, this top method is an option to you. Of course, you could go out and buy a transmitter as well. And using this method at the top is the way that you connect all of those pieces up. Basically what happens here is the input system feeds the controls into the adapter. The adapter interprets those controls and puts out what's called a PPM feed to the transmitter. PPM's the standard way that RC vehicles, that commands are issued to an RC vehicle. So feeding that into the transmitter allows it to be passed on to the RC vehicle. So the trainer port idea is piggybacking on the concept of using two transmitters in a training scenario. So when an instructor might be teaching a student how to operate an RC vehicle, you can connect two transmitters together. One is the master, which is held by the teacher, and the other is the slave, held by the student. And when the teacher is ready for the student to take control of the vehicle, they would flick a switch on the transmitter and allow input from that student transmitter, which is cabled into the teacher's transmitter. And at that point, the student can then use their transmitter to operate the vehicle. If at any point the teacher needs to take control back, they can do so just by flicking the switch, and the teacher can then use their transmitter to directly control the vehicle. So it's a great way for a teacher to train someone how to fly a drone or how to fly an RC plane, for example. And we're using it here as a means of providing that input into the transmitter so that it can then be passed on to the vehicle. So the second option is this one at the bottom, where the input system is going into the adapter in the same way as the top option, but instead of being connected into the trainer port of a transmitter, the adapter feeds that PPM information directly into this little transmitter module, which is referred to as a multi-module because it's capable of communicating with a whole range of different protocol, radio protocols for RC vehicles. So we went with this option just primarily because we felt it was simpler and didn't require the use of an external transmitter cabled into the trainer port. But both of these options do work, and I guess it's up to you which way you want to go with it. So looking at the input systems now, to show you what the options might be for the way that you can provide control input to the adapter. So it's worth saying that the way this Arduino-based adapter has been configured is to be compatible with Xbox-based controllers, but it's very feasible to reconfigure the code in the Arduino to accept commands from PlayStation, from just a generic HID joystick. The USB host library allows input from a whole range of different devices, and I've just chosen to configure it to receive input from Xbox-based controllers, but there's nothing stopping you going in, adapting the code and using any gaming controller or joystick that makes sense to you. So the simplest input system that that this adapter can accept is from just a basic Xbox One controller. So by just connecting the USB port of the Xbox One controller into the adapter allows by default, the left analog joystick to control the vehicle. I have configured some of the other buttons as well to do certain functions, which I'll go through later when I go through the code. But very simple option is basically just to wire in a standard Xbox One controller. By extension then, the Xbox adaptive controller can be plugged into the adapter. So the system just sees an Xbox One controller and an Xbox adaptive controller more or less as the same thing. But using the adaptive controller provides a huge opportunity for the system that the person uses, the joysticks, the buttons, whatever, to be very highly customized to their needs. So I went with this option because it just creates the greatest flexibility for the user to configure the system how they want. So by having the adaptive controller plugged in, you can then, say, plug in a hand-operated joystick. And that simulates or replicates, I should say, the function of the left analog joystick by having that plugged into the left USB port of the adaptive controller. Similarly, you could have two hand-operated joysticks to give you the 4 axes of movement. I haven't done this yet, but there's really no reason why you couldn't use this 2 joystick operation to fly a drone, that would normally use 2 sticks, and basically this system's just providing that 2-stick input. I haven't written the code to accommodate 2 joysticks, so if you wanted to do that, you would have to adjust the code yourself. But it's the code's so flexible that it allows that opportunity. Another option, if you can't use your hands, is to plug in a Quadstick into the left USB port, and again that replicates the use of the left thumbstick on the Xbox One controller, and also gives you a couple of buttons by using the sip and puff straws. You could, of course, plug the Quadstick into the left USB and have a hand-operated joystick plugged into the right USB. And again, that would expand you to being able to use drones and planes potentially. Another option is to use the FreedomWing that AT Makers put together, which I've provided a link for in the description. This is a device that is focused on gaming, and it allows you to plug a wheelchair joystick into an Xbox adaptive controller and use that as the joystick input for your games. So by extension, we can use that option to allow the use of the wheelchair joystick as the input method for operating an RC vehicle. I'll provide a link to the FreedomWing in the description. I'm not going to go through how to build that. It's a bit of a job to piece one of those together. But once you've got it, it's a pretty powerful and useful little tool. So it's worth saying that the FreedomWing only works with specialty controls joystick options. So something like a chin control joystick or one of the more specialized joysticks. Doesn't work with just the standard JSM joysticks, because there's no 9-pin plug to plug into the FreedomWing. So just bear that in mind. It's not every single wheelchair joystick available. It's only the ones that are referred to as specialty controls. Of course, using the adaptive controller, you then get the option of plugging in accessibility switches, which can be used in conjunction with a joystick. Like I said, I've assigned some functions to the buttons. So plugging in the external accessibility switches provides access to those functions. So no matter what input system you decide you want to use, you will need some things. There's a whole bunch of things that are optional, but there's a couple of things that are essentials, and I'm just going to go through them now. So the first is to have an Arduino Uno. I did toy around with the idea of different boards, trying to make it a bit smaller, but you need to have the ability to provide power and have a USB input for the input system. So I wasn't able to think of a different configuration that allowed those options without having to do any soldering. So this is the option that I'm recommending, is to use an Arduino Uno with a USB host shield stacked on top. So with the two together, it looks like the picture on the right there. Power goes into the Arduino Uno's USB port, and then the input from the Xbox system goes through the USB host shield. So this is a must-have. It's a bare minimum for getting the system to work. Another bare minimum, if you want this to be portable, is to have a power bank, preferably with two USB ports, and that's because in some circumstances the Xbox Adaptive Controller also requires its own power supply. So having two USB ports on your power bank is a good thing to have. And secondly, you'll need a USB-A to USB-B cable, and in this instance short is good because you're just powering the Arduino, and so having the power bank located next to the Arduino with it via a short lead just keeps everything nice and tidy without having masses of cable everywhere. So things that you may need, if you want to have a screen on your adapter, you'll need to use, what I would recommend using is an Adafruit RGB LCD shield. The code that I've put together just provides some information on the screen, such as the trim setting, current trim setting, and also for the sailing boat, some information around what the sail position currently is. Once the boat gets a little bit far away, it can be hard to judge what the sail trim actually is, and because the way it's configured, you don't get the feedback from the joystick itself. Having some information on the screen can help you to know what's happening if you can't see it quite clearly. It's totally optional. You don't have to have the screen, so by all means skip it if you're just trying to go with the bare minimum. But it's an optional extra that just gives you some info when you're out operating the vehicle. I chose to use extra long breakaway male header connectors to solder onto the RGB LCD shield, and that's because it allows the wires that you need to run through to the multi-module to be soldered onto the pins a little bit easier. If you just use the short headers, you don't get these. It's not as easy to solder on the wires, so I just did that for that benefit. And having the extra long pins on the bottom also make sure that the LCD shield stands up above the USB host shield, because it stacks on top of this. So you end up with a triple stack device where you've got the Arduino on the bottom, the USB host shield, and then the LCD shield stacked on top 3 stories high. I have designed a 3D printed case to put it all in, which is designed around having the LCD shield stacked on top, and having a slot for the multi-module to fit into there. So I'll provide a link in the description for that model on Thingiverse, so you can just download that and print that if you choose to have that. Again, not an essential, something you might want to have just to keep everything tidy and protected. So depending on the transmission system that you want to go with, you may or may not need these components. So if you decide to go with the trainer port option on a regular transmitter, these are the things that you'll need. So in addition to the Arduino and the USB host shield, you'll need a 3.5mm mono socket, and a couple of wires to connect that socket onto the board. So you would then need a mono cable to join the transmitter to the Arduino using that mono socket. That cable, it helps for that to be a little bit, have a little bit of length on it, just so that you can have some flexibility with where you position things. But really any length is fine. You'll need a compatible transmitter that's got a trainer port on the back. I've found that the Tyrannus range is pretty good, and I haven't had much experience outside of that, so I'm sure there's a whole swathe of options there. But really anything with a trainer port on the back should be suitable. And then the last thing that you'll need is to ensure that whatever receiver that's in the RC vehicle is going to be compatible with that transmitter. So I'll leave that up to you to figure that out, because it's entirely dependent on what the transmitter is as to which receivers are going to be compatible with it. So if alternatively you want to use the multi-module option rather than using the trainer port option on a transmitter, these are the pieces that you'll need. So the first thing is the multi-module itself, which is an iRange X IRX4 Plus. There's a link in the description for where you can buy that. Most people get them from Banggood or from eBay sellers. You'll need a strip jumper cable with one end female, and what we're going to do with that is cut off the other end, so it doesn't really matter what's on this end as long as one end is female. And we want them to be in a strip so that it keeps all the cables together. You end up with like a ribbon cable concept like you would have in inside a computer. It just kind of keeps everything tidy. If you've got 5 separate cables, it will still work, but it'll just be a little bit messy. But having them all joined together in a strip just gives you a nice clean result. You'll need some more extra long breakaway male header connectors, and the way we use those is to plug them into the female ends of these cables to then plug into the back of the multi-module. And you'll also need a compatible receiver, a receiver that's compatible with the IRX4. Now the point of the IRX4 is that it's compatible with a whole wide range of different receivers. That's its purpose in the general market. So it's generally pretty easy to find a compatible receiver. We've been using the FlySky range of receivers and found the compatibility to be very good. It binds with that binds with that transmitter very well. FrSky, all the other major brands of receivers are meant to work. We just don't have experience with those. Because we're mostly using 2-channel RC vehicles for our application, sailing boat, remote control car, there are only 2 channels. We've just been using the FlySky GR3E receiver. It's a 3-channel receiver, and it's adequate for our purposes. I have used a 6-channel receiver from FlySky, and that worked just as well. So switching over to the input systems now, these are the things that you may need depending on what choice of input system you're going with. So if you're just wanting to use a regular Xbox One controller, you'll need the controller itself and a USB-A to micro USB cable. In this instance, long is good because you want a little bit of flexibility with where you hold the Xbox One controller relative to where the adapter would sit, say on your lap or in a bag or whatever. If you want to use the adaptive controller option, then you'll first need to have an adaptive controller itself and then a USB-A to USB-C cable. In this instance, short is good because you tend to position the adapter and the controller close to each other, and just having a short cable there keeps everything tidy. So if you're then extending the adaptive controller to use joysticks, you'll just need any USB HID joystick and one or two depending on your purposes. Some of the options that exist are the Quadstick Ultra Stick, the Warfighter Engage range of joysticks such as the Joystick L or the Mini Sticks. The Logitech Extreme 3D Pro will work, and also the PDP one-handed joystick will work. Any of these can be plugged into the USB port of the adaptive controller and provide analog joystick input. If you're wanting to just use accessibility switches or use those in addition to a joystick, you'll just need to supply the accessibility switch of your choice, really anything that terminates with a 3.5mm mono jack. The Logitech adaptive gaming kit's pretty hard to go past in terms of cost effectiveness, but any sip and puff switch, proximity switches, wand switches, jelly bean, spec switches, all of those will work. So you just need as many of those as functions you require. If you're wanting to, instead of using a hand-operated joystick, use a Quadstick, you'll need the Quadstick FPS device. You'll need a USB-A to USB-B cable, which one of those comes with the Quadstick, and long is generally good so that you've got freedom of position of that joystick. You'll also need to have a USB-A to 5.5mm cable, barrel cable. This is to provide power to the Xbox adaptive controller from the battery bank. So if you're using the Quadstick with the Xbox adaptive controller, the adaptive controller needs its own power supply. It's not enough to run off the Xbox adaptive controller's battery or the power that's coming from the USB host shield. What you don't want to have on this cable is any kind of power converter. I've noticed that you can buy a cable that looks like this, that has a power adapter or a power converter in line. So it converts 5 volts up to maybe 9 volts or 12 volts or whatever. You definitely don't want that option. You just want it to be just a straight through cable that just carries 5 volts. If instead of the Quadstick you're wanting to use a wheelchair joystick to operate the adaptive controller and therefore operate the vehicle, you'll need to have a compatible wheelchair joystick, something in the specialty controls range, and it needs to terminate with a 9-pin D-sub connector. You'll also need to get yourself a FreedomWing, which is what allows the wheelchair joystick to be plugged into the adaptive controller, and there's a link in the description for the website that'll give you some information around how to build one of those for yourself. You'll need a USB-A to micro USB cable for connecting the FreedomWing to the adaptive controller, and similarly to the Quadstick, you'll need a USB-A to 5.5mm barrel cable. And again, let's make sure there's no power conversion in the cable. And again, that's for the same reason as a Quadstick. It's because this system with the FreedomWing and the wheelchair controller needs the Xbox adaptive controller to have its own power supply. So talking about that power supply, this is the way that the pieces get connected together. So if you're wanting to use the Quadstick, or if you're wanting to use the wheelchair joystick with the FreedomWing, you'll need to connect these devices in this way. So having the battery bank with a powering the Arduino system, the battery bank also powering the Xbox adaptive controller, and then the data communication between the controller and the Arduino via a USB-C to USB-A cable. What I'll demonstrate now is how the various pieces of the system fit together, starting with the setup where we've got the Arduino going into the trainer port of a radio transmitter. So starting with the Arduino adapter, we've got the Arduino Uno on the bottom with the USB host shield stacked on top. They just separate. The USB host shield comes with the pins already soldered on, so I didn't have to do that soldering, which was nice. And they just stack together, just like so. We then have a couple of jumper cables with the male pins on one end, and the other ends are also male pins, but I've soldered those onto the terminals of this 3.5mm mono socket. And so the male pins go into the USB host shield, one cable into the ground pin, and put that back in, and the other one goes into pin 3. So just like that. And what we want is the ground pin running through to the through to the sleeve of the mono socket, and we want the signal pin, pin 3, running through to the tip of the mono socket. Okay, so we then take the mono cable, plug that into the trainer port of the transmitter, and the other end into the socket, the Xbox adaptive controller into the USB host shield's USB port, and the battery bank into the Arduino's USB port. Turn on the transmitter. And always turn on the car last once you've got everything else turned on. Okay, so now we've got control. You can see the steering changing there, and we've got forward control by pushing the joystick up, and reverse control by pulling the joystick back. Okay, and then if we switch the transmitter off trainer input, then I can control the car just using the transmitter directly. So we've got left and right steering there, and accelerate. This next setup adds in a couple of extra elements. We've still got the Arduino and USB host shield here. We're going to add in the RGB LCD shield from Adafruit and use the multi-module as the transmission method to the car, rather than going straight to the trainer port on the regular transmitter. And we're also going to add in the 3D printed case. So the RGB LCD shield comes in a kit, and you have to assemble that. What I've used is extra long header connectors, so that you've got an easier location to solder on this ribbon cable. So I had a strip of about 20 of these jumper cables, and I just tore off a strip of 5 and then cut the ends off this end, and soldered them onto those header connectors. What you want is, if you have a strip of 5 cables, you want cable 1, which is white here, to go to pin 3. You want cable 3 to go to the 5 volt pin, and you want cable 4, which is blue, to go to ground. And cables 2 and 5 are unused, but there's 5 female connectors on the back of the multi-module, and I just found it easier to keep 5 pins so that you didn't get them misaligned and end up putting positive voltage somewhere where you didn't want it. So the LCD shield stacks on top of the USB host shield to make a triple stack device. And then using the 3D printed case, we just feed this connector. Sorry, I should have mentioned that at the end of this cable is actually, the way I've done it is to have female, to have that terminated with female connectors. Sorry, I keep losing my focus here. And to then plug in some male header connectors again onto the end of those. The reason I've done that is because the standard jumper cables that terminate with male pins, they're just a bit too short to be able to reach all the way into the back of the multi-module and to go into the contacts. So I just found that I had to use extra long header connectors, which meant using female cables here and using a male-to-male connector on the end. And it also helps to keep them tidy. You'd probably have to glue these 5 connectors together if it wasn't for using this strip of male headers. So feeding that into the 3D printed case, there's a little slot there that this cable feeds into, and then the whole thing drops down into there, and there's 4 little lugs that the Arduino just sits on. So you just kind of gently pull that cable through. The nice thing about the case is that there shouldn't really be any tension on those soldering joints, so that they probably shouldn't wear out. Feed that cable then through that extra hole, and then the multi-module sits into there. So you just have to get it aligned so that the number 1 cable is at the top of the multi-module, just like that. And the whole thing rests back down into place. Okay, and then there's a little cover that seals the whole thing up. I have left a little window here in case anyone. I just found sometimes it is a little bit tricky to get the Arduino stack into there. So sometimes doing it separately, putting the Arduino in by itself and then putting the other 2 on top, is another way to get it into the case. And just having a little viewing window there allows you to make sure that you've got your pins lined up correctly. So that then, again, the Xbox adaptive controller plugs into the USB host shield, which is this window. The battery bank goes into the Arduino's USB port. And now we've got some information on the display which helps us to know what's happening with the car. We've got speed settings set to 1 and the steering trim set to 0. So now when we turn the car on, again we've got control of the car from the joystick. And if we use the D-pad now to dial up the speed, so that's now speed 2, I get a faster speed, and if I go all the way up to speed 4, it'll be very twitchy. I'll probably have to hang on to the car. Okay, and still steering left and right. We've also got steering trim. So if you go left and right on the D-pad, you get an increasing number there, and you can see the steering is shifting to be biased towards the left. And then pressing either of these 2 buttons will get you back to reset steering, and then trimming the other way, and then reset. The next setup is with the Quadstick rather than the hand joystick. So this now requires an extra power supply from the battery to the Xbox adaptive controller. So if we add that one into the other USB port on the battery bank and plug that into the power port. Now the Quadstick goes into that same USB plug on the adaptive controller, the left hand side, and finally power up the adapter. Always with the car off, so turning the car on now. So now we have up is accelerate on the joystick, left and right is steer, and down is reverse, up and then brake. Adjusting the trim using the Quadstick, you would use the left and the right channels. So blowing into the left channel, you can see the trim being adjusted, and blowing into the right channel, adjusted back down. So that's blowing into the left and the right, blowing left and right. Sipping left or right resets the trim back to 0. And lastly, I'll show using a wheelchair joystick using the FreedomWing adapter. So we take the FreedomWing, plug the USB cable into its USB port, and then the other end into the Xbox adaptive controller. Again, you need the power connection from the battery bank to the adaptive controller in order to basically power the joystick. And then plug the joystick into the FreedomWing's 9-pin port. Okay, adapter on. And again, up to accelerate, left and right to steer. And again, up and down on the D-pad to adjust speed, left and right to adjust trim. I've written sketches for 2 different RC vehicle types, which are cars and sailing boats. I've focused on 2-channel vehicles, mostly because my main objective has been to cater to people who need to use either just the Quadstick or a large single joystick, like a wheelchair joystick, as they have only access to 2 axes of movement. The first sketch we'll go through here is for the car, mostly because it has the most straightforward controls. The overall purpose of this sketch is to read the input from the Xbox controller, interpret and remap that data into PPM format, and that includes assigning particular controls to particular RC channels, and then to output that into a PPM feed, which is issued and fed from the Arduino digital pin. A PPM feed it's basically a string of electrical pulses of varying timings. Each channel is a pulse, and the value of that channel is indicated by the relationship between the pulse and the pauses between the pulses within the overall frame. PPM values usually range from 1000 to 2000, and these values are used differently depending on the purpose. And for example, when used to control steering, for example, 1500 means that the steering is centered, 1000 means fully left, 2000 means fully right. For a different purpose, like throttle on a plane or a drone, 1000 usually indicates 0 throttle and 2000 full throttle. And for throttle, say on an electric RC car, 1500 means 0 throttle, where 1000 means full reverse and 2000 means full forward. The way these sketches manage the PPM feed is to create an array with 8 elements, representing up to 8 channels. We only need 2 of these channels for a 2-channel RC vehicle, but because I'm using someone else's code and there's no real reason for me to change it, I've left it so that the PPM feed still outputs all 8 channels. It's just that only 2 of them vary based on input. So for the car, channel 1 carries the information for steering, which is position 0 in the array. Channel 2 is for throttle, and that's position 1 in the array. So anytime you see PPM 0 in the code, that's related to steering, and anytime you see PPM 1, that's related to throttle. So the inclusion here relates to the USB host shield library. Because the adapter uses a USB host shield for the Xbox input, you'll need to download and install the associated library. So to do this, you just visit this link to download the zip file from GitHub, and then you install it by going up to Sketch, Include Library, and then Add Zip Library. So I've already done that on this computer, so you can see once you've done that, you'll have this USB host shield library listed in your libraries list, and you'll also be able to see some example sketches if you go to File, Examples, and then down here there's the USB host shield library example sketches. And in particular, what you might notice is that there's one for the Xbox. When I when I wrote this sketch, I relied heavily on the Xbox One example sketch, which is provided with the Host Shield library. So anyone wanting to make any major changes to this sketch, it'd be a good idea to familiarize yourself with this example, because I just found it really helpful in terms of how you can, assign a button action to an output on the vehicle. So stepping forward, we have some more inclusions for the RGB LCD Shield from Adafruit. And again, this is another library you'll need to download and install. So you need to visit this link, download and install that library, and add it the same way you did the Host Shield library. Then there's some definitions for LCD colors, and some variables that you may want to change down here. So the one that you may want to look at changing is speed settings. So to help beginners, the car has 4 different speed settings, with settings 1, 2, and 3 being speed limited and speed 4 being unlimited. And this variable here determines what the default speed setting is on boot. And I've elected to go with speed 1 as the default, so that when you turn on the adapter, it automatically goes to speed 1, and then you can dial it up to speed 4. It just kind of keeps it safe for a beginner to start using right out of the box. So the next section sets up the PPM output, and this is the code that I've borrowed, and I must say I really don't understand it. The one thing to note is that it's here that the sketch specifies the signal pin which is used for PPM output, right here on SIG pin 3. So if for whatever reason you wanted to use a different pin number to output from the Arduino to the transmitter, then you would change that here. So moving down to the loop now. The first thing that the sketch does is to set the steering. So most cars won't drive perfectly straight, so there needs to be the ability to trim the steering, which creates a bias or an offset to one side, so the car that naturally pulls to the left or the right can be corrected to drive straight. This sketch achieves this by watching for certain button clicks, and either adds or subtracts from a trim value. So this steering trim either has a value added to it or subtracted from it depending on the button clicks. So the buttons for the user to adjust the trim are left and right bumper, and left and right on the D-pad. It might look strange, but I've also added L3 to trim towards the right, because this is the left thumbstick click. And the reason I've done that is because this is one of only a few buttons that's available to assign when the Quadstick is plugged into the left USB port of the Xbox adaptive controller. So with this configuration of L1 for left trim and L3 for right trim, that allows a Quadstick user to trim left and right by doing a puff into the left channel of the Quadstick and a puff into the right channel of the Quadstick. If you want to reset the trim to 0, you can either press back or start, which is these ones here. So doing either of those actions will reset the trim to 0. And for a Quadstick user, that is done via either left or right SIP. So with the trim value calculated, the raw input from the joystick is now captured in this little section here. So the Xbox joysticks feed a value into the adapter that is going to be somewhere between minus 32,768 and positive 32,768, with 0 being a center joystick, minus 32768 being fully left on the joystick, and plus 32768 being fully right. So here the script is watching the X value, the left and right action of the left thumbstick. And when the joystick input is between 0 and 250, so when it's less than, 2,500, it basically ignores that input. And it does this else section. So if the input is greater than 2,500, then do this. Otherwise, do this. And what this is doing is setting the ppm value to 1,500 plus or minus steering trim, which basically means centered. So any movement less than 2,500 means that the vehicle is given a center steering command. So it's effectively creating a deadband effect. Any values over 2,500 are considered outside the deadband, and so then the script does this remapping process. So fully left gets remapped to 1,000, which is a ppm value, and fully right gets mapped to 2,000. And this mapping then obviously does everything in between on a sliding scale. And then this calculation or remapping is fed into the ppm 0 position, so the steering ppm value. So that's how left and right on the joystick gets converted into a ppm value on channel 1. So next, the script looks at throttle. And for this is where I've added in the speed control to help beginner drivers. So the speed control is achieved by changing the joystick value, remapping, so that the maximum joystick throw only results in a less than maximum ppm value. So if the speed setting is 1, the maximum forward ppm value is only 1590, and the maximum reverse value is only 1410. So rather than being able to issue a maximum value of 2000, it only issues 1590. The speed selection setting is adjusted by pressing the up button or the down button on the D-pad. And unfortunately, I couldn't find a way to allow a Quadstick user to do this. So this is something that a person assisting the Quadstick user would need to perform directly on the Xbox Adaptive Controller. So if you like, you can play around with these settings. If you're finding that with your particular car, 1590 is too fast or too slow for a speed 1, you can either dial that up or dial it down. What you do need to do is keep these numbers symmetrical either side of 1500. So this is 90 above and this one's 90 below. If you wanted it faster, you'd have to make this one, say, 100 or 110 above 1500 and this 100 to 110 below. Otherwise, the centering of the throttle won't be at 1500, it will be offset. So once the speed setting is selected, the script then again captures the raw input from the Y-axis of the left joystick, and again creating a deadband by ignoring any input below 2500, and then remaps it according to the speed setting, which it does on that line, and then records that into the into position 1 of the ppm array. Next is a large section of commented out code. It's just a copy paste really from the Xbox One example sketch, and I've left this here just as a reference for how you could go about assigning a button for a particular purpose. So if you wanted to use the sync button or the Xbox button to do something in particular in your script, this is the function that you would call to be able to do that. So I've just left it there as a reference. Further down is a short bit of code that manages the backlight for the LCD. I've just set it so that when an Xbox controller is connected, the LCD will shine with a green backlight, and when it's disconnected, you'll have a red backlight. I've also put in a safety feature here that if the Xbox One controller is ever disconnected, that the ppm1 value, the throttle, will be set to 1500 or 0, so you won't accidentally have the car taking off because it's somehow been fed a different value than 0 throttle. A little bit lower is a section of commented out code that allows you to see the ppm output in the serial monitor for debugging. If you want to see a particular channel, it's just a case of uncommenting that particular those particular channels, and then opening the serial monitor while you've got a joystick plugged into the Xbox adaptive controller and the Xbox adaptive controller plugged into the to this adapter. I have had some funny behavior when trying to actually operate an RC vehicle with this code uncommented. So I wasn't able to really pin it down. So I think it's best that if you want to do some debugging, by all means go and uncomment and then look at the serial monitor. But whenever you want to actually operate a vehicle, it's probably best to re-comment that code just to prevent any unwanted actions. The next bit here is some more code related to the ppm output, which is, again, code that I borrowed, so I don't totally understand it, but I haven't had to adjust anything to get it working, so I've just kind of left it alone. And then lastly, there's a couple of functions which manage updating of the information on the LCD. The first to update the steering trim information, and the second to update the speed setting information. I was noticing some major latency issues when this code was inside the loop. I originally put this code inside the main loop, but I pulled it out into separate functions just to manage some latency issues. So these are only called once when the settings are adjusted by the user. Switching over to the sailboat sketch now, much is the same except for just a few key differences. The first is that the sailing boat sketch uses channels 1 and 3, channel 3, as that seems to be the default for RC sailing boats rather than the channels 1 and 2 that the cars tend to use. Steering is managed the same as for the car, including the trim setting. However, due to the idiosyncrasies of using a rudder, the directions are intentionally inverted here. So rather than it being mapped from 1000 to 2000, it's the other way around, so 2000 to 1000. And that's so that when you push the joystick left, the boat turns left, rather than it being that pushing the joystick left pushes the rudder to the left, because that would make the boat go to the right. Lastly, sail set is, so adjusting the sails is very different to throttle. So this section of code is where it's most different to the RC car. On a standard controller, the sail trim or the sail setting is usually managed with an unsprung joystick. So basically a joystick that preserves whatever position you move it to and then doesn't self-center. The Quadstick and other gaming joysticks, however, do self-center, and there's no real way around this with the joystick itself. So I've written code that accommodates this difference. Basically, whenever the joystick is deflected on the y-axis outside of the deadband, the value of ppm2 is adjusted up or down. And then when the joystick returns to center, this value stops being adjusted and remains static. So the increment that I've set here is 5, meaning that every time this script, this sketch runs through its loop and the joystick is deflected in the y-axis, the ppm value will be incremented by a value of 5 until it hits either a maximum of 2000 or a minimum of 1000. So if you find that when with your particular setup, with your particular boat, that the joystick deflection is causing the sails to move either too fast or too slow, I would suggest just changing this value up or down. A higher number would mean a faster adjustment, and a lower value a slower one. The code also provides a degree of proportional adjustment in that if you perform a partial throw, so anything over 7,500, but less than 25,000, that'll result in a slow adjustment of the sails. But if you throw the joystick further, so that you're over 25,000, but basically between 25,000 and 32678, you'll get a faster adjustment. The other thing is that I've also added in a couple of button clicks, which what they do is to set the sails either all the way in or all the way out in one go. Generally, when you're tacking upwind, you want the sails all the way in tight, and when you're going downwind, running with the wind, you want them all the way out. So what I've provided here is just an easy way to get to the extreme settings of the sail set. And you do that by either pressing A or B on the controller, which are center sip and center puff on the Quadstick. So in order to use the iRange X4 with the adapter, you need to update the software that's installed on the iRange X. So to do that, you visit this website, this part of GitHub, and it's the software that you want to install on your computer is called Flash Multi, and it's currently version 0.6.1. So you scroll down to the bottom, and there's a download for a zip file. So just download that. Extract that just into your downloads folder. And then run this software called Flash Multi. So what you need to do now is to go back and find the appropriate firmware for your device. So the easiest way to do that is to come to this Help menu and say Get Multi-Module Firmware. That will open another browser window on the multimodule.org site, where you put in the details of your multi-module. The one that I'm using and recommending is the iRange X IRX4. So click that, and then it gives you a bunch of different firmware versions that you can download. You'll notice that the first three are PPM and the second three are Cerebral. The one that we want is one of these three PPMs, and the other difference is the channel order. So the one that we want is AETR, so it's the first one. So download that. Again, just save it into your downloads folder. So now come back to the software, and now you want to browse and find that file that you just downloaded, the firmware file. So it's found it, it's ready to go. So what we need to do now is plug in the iRange X module into your computer. So just use a USB port and plug in via the port on the face of the iRange X. It's just next to the yellow dial. So I'm plugging that in now. And the software has detected that. So I've already got this software on this device, so I'm just doing this again for demonstration. So if I read the module, it will bring up the software that's currently running on it. And I can now write this firmware version onto it by going right. Let's hit OK. And all going well, you should get a firmware written successfully prompt. Now that you've got the firmware installed on the multi-module, it's time to try and bind the multi-module to the receiver in the vehicle. I found this a little bit challenging. If you go to the multimodule.org website, it says that this module should be compatible with the receiver that was already in this car, which is a Traxxas. I tried really hard to get them to bind, and for whatever reason, it just wouldn't do it. So I've switched out the receiver for a FlySky one, which is one of the more default protocols in the multi-module, and I've had much better success with that. So that would be my recommendation, is to purchase a FlySky receiver in order to work with the multi-module, as I found that the easiest binding process. In order to do the binding, the FlySky module needs to have a little binding jumper attached into that channel. It's in channel 3, I think. So you place that binding jumper in and then turn on power, and you'll see the receiver is flashing with a red light. You then make sure that you're on the correct protocol on the multi-module, and the protocol is selected by turning that yellow dial. So you just need to refer to the table on multimodule.org to know which is the right position. Mine is, for FlySky, it's basically position 1 in bank 1. So with that correctly positioned, hold down the bind button and then power on. And you'll see the binding light on the receiver has gone solid, which indicates that the multi-module and the receiver have now been bound together. So then we turn off the car again, turn off the adapter, unplug the binding jumper, and now power on the adapter. Power on the car, and the two are now bound together. So if you've managed to stick with me to the end, that's just about everything you need to know to get you up and running with your own adaptive RC controller. Enjoy!